Today's video, we're going to talk about entropy. Entropy is a state function that we use to help explain spontaneity. So what is spontaneity? Well, if we describe a process that's spontaneous, this is a process that occurs without continuous input of outside energy. In other words, once you get it started, it will just continue to happen. A spontaneous process, it's important to notice, just because a process is spontaneous doesn't mean it's necessarily fast. There are some processes that are spontaneous that will also move very slowly. The spontaneity of a process can't be predicted by the first law of thermodynamics only. The first law of thermodynamics, remember, says that energy can't be created or destroyed in the universe. So that means if you have a closed system, no energy can be created or destroyed inside that system. So the total change in energy is zero. Okay, here's a system, very simple one. We have some material, let's say it's a block of metal at 40 degrees, and the other part of the system is a block of metal at 20 degrees C. One thing that could happen is energy could transfer from the hot block of metal to the cold block of metal, and they would reach this thermal equilibrium at 30 degrees C. We know that that happens. But here's another possible thing that could happen. Energy could transfer from the cold thing to the hot thing, and the hot thing gets even hotter and the cold thing gets even colder. We know that that first thing spontaneously happens, but the thing on the bottom, that event does not happen spontaneously. So there has to be something else going on here, and that's where entropy is going to help us with these decisions. It is true that lower energy systems are more stable, so they do tend to result from spontaneous processes. So if you have an exothermic reaction, that tends to be spontaneous. Many times it is. And an endothermic reaction tends to be non-spontaneous. But as we saw in the example with the heated up blocks, there has to be more to the story because both of those processes resulted in no change in enthalpy in the system. And we know that some endothermic changes are spontaneous. For example, the evaporation of water spontaneously occurs at room temperature. If you spill some water on a surface, a countertop or something like that, go away for a while, without adding extra work from the outside over time, that water will spontaneously evaporate. The melting of ice at room temperature is also a spontaneous process. Dissolving of lots of salts will spontaneously occur. Just dump it in there, stir it around, and it spontaneously dissolves. So there has to be this other factor to consider, and that's the entropy that we're about to talk about. Now, to start to get an idea about what entropy really is, first of all, you may have heard that entropy is like general messiness or disorder. And in everyday life, people sometimes talk about high entropy as being just things are disorganized or a mess. That's an everyday kind of use of that term, but it's not correct. That's not what we are talking about in science when we're talking about entropy. So we're going to start out by talking about probability, microstates, and macrostates to begin understanding this in a more rigorous way. The sum of the two faces rolled is what we will call the macrostate. How many macrostates are there for two dice? Well, you can't get a 1, but you can get a 2. You can get a 3, 4, a 5, a 6, a 7. You can get an 8. You can get a 9. You can get a 10. You can get an 11. You can get a 12. But you can't get a 13 or a 14 or anything higher than that. So there are 11 macrostates, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. The individual combinations that result in that macrostate is a microstate. How many microstates are there for two dice? We also want to look at which macrostates are most and least likely to occur. That should say macrostates, not microstates. So let's look at the possible macrostates and which microstates will yield those macrostates. For 2, a 1 and a 1 is the only microstate that will lead to that macrostate. For 3, a 1 and a 2, or a 2 and a 1. For 4, 1 and 3, 2 and 2, and 3 and 1 will all yield the macrostate of 4. For 5, 1 and 4, 2 and 3, 3 and 2, and 4 and 1. For 6, 1 and 5, 2 and 4, 3 and 3, 4 and 2, and 5 and 1 will yield that macrostate. For 7, 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, and 6 and 1 will yield the macrostate of 7. For 8, a 2 and 6 will do it, 3 and 5, 4 and 4, 5 and 3, or a 6 and 2. For 9, a 3 and a 6, a 4 and a 5 and a 4, and a 6 and a 3 will give you 9. For 10, a 4 and a 6, a 5 and a 5, and a 6 and a 4 are the 3 microstates that will give you that macrostate. For 11, it's a 5 and a 6, or a 6 and a 5. And for 12, there's only one microstate that will give you 12, and that's a 6 and a 6. So if we look at the total number of microstates that there are, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. There are 36 possible microstates here. What's the probability of a macrostate of 2? Well, there's only one possibility that results in that macrostate. So that's a 1 in 36 possibility. This is a 2 in 36 chance. 3 in 36, 4 in 36. For a 6, it's a 5 in 36. For a 7, there are 6 microstates that will get you a 7. A 5 in 36 chance, 4 in 36, 3 in 36, 2 in 36, and 1 in 36 again. So we can see that the most likely macrostate is a 7 because there are more microstates that will give you a 7. People who play dice know that 7 is the most likely macrostate. So what makes a macrostate more likely? More microstates result in that macrostate. So the likelihood of a macrostate in energy distribution is higher when more microstates can result in that macrostate. Boltzmann theorized a quantity that's called entropy, we abbreviate that with a capital S, that could account for this. Processes where the change in entropy gets greater tend to be spontaneous because there are more microstates after the change than there were before. And conversely, processes where the entropy change is less than 0, in other words, where there are fewer microstates after the change, they tend not to be spontaneous. Boltzmann did some more detailed work on this, and he found out that the entropy of any system is proportional to the natural logarithm of the number of microstates. So W here in this equation is the number of microstates. R is the universal gas constant, and Na is Avogadro's number. That ratio of R to Avogadro's number is called the Boltzmann constant, Kb. So this simplifies to S equals Boltzmann constant times natural log of number of microstates. Okay, now let's start to look not at dice, but particles distributed in space. So we have, in the left-hand side on the top of this chart here, we have one particle, and it's trapped in one of the flasks. The valve between the two are closed. If we open that valve and give this particle some time to randomly move around, remember there's random motion involved here, there are 2 ways that we could find this system after the particle's been moving around for a while, 2 microstates. One microstate is the particles on the left-hand side. The other microstate is the particles on the right-hand side. So we had only one microstate before, and now we have 2 microstates that are possible afterwards. So opening up that valve increased the number of possible microstates. Now consider we have 2 particles in 2 flasks. At first, there's only one microstate, and that is both particles are in the left-hand flask. But if we open up the valve and let the particles randomly move around, there are 4 possible microstates that could exist after this change. One is both particles are still in the left. We could have pink and left, blue and right. We could have blue and left, pink and right, or we could have both particles in the right. What if we have three particles in two flasks? Before we open the valve, of course, there's one microstate. Afterwards, we could have all three still in the left. We could have pink and purple in the left and blue in the right. We could have pink on the right and blue and purple on the left. We could have blue and pink on the left and purple only on the right. We could have purple only on the left, blue and pink on the right. We could have pink only on the left, blue and purple on the right. We could have blue only on the left, pink and purple on the right, or all three particles could be on the right. Those are the only combinations that we could have, and there are 8 microstates. In the first example, where we had one particle in 2 flasks, after we opened the valve, we found out that 2 to the 1, or 2 microstates were possible. In the second example, where we had 2 particles in 2 flasks, we found that 4 microstates were possible, which is 2 to the 2 power. Here, we have 3 particles in 2 flasks, and we find that 8, which is 2 to the 3rd microstates, are possible. So what it looks like is the number of flasks, in this case 2, raised to the number of particles, let's call that n, is the number of microstates that are possible. So what if we had 10 particles in 2 flasks? Well, the number of microstates, W, remember that is, would be 2 particles raised to the 10 flasks, which ends up being 1,024 different microstates. How many microstates would be possible for a mole of particles in 2 flasks? Well, that would be 2 raised to Avogadro's number. Here's a slightly more realistic question. What is the entropy change for 1 mole of atoms expanding from 1 liter to 2 liters of volume? So let's take a flask as being a liter. State number 1, what's the entropy? Well, it's R divided by Avogadro's number, that's Boltzmann's constant, times the natural log of 1 raised to Avogadro's number. That's, of course, 0, because 1 raised to anything is 1, and the natural log of 1 is 0. State number 2, the entropy is going to be R divided by Avogadro's number times the natural log of 2 raised to Avogadro's number, which is equal to R times Avogadro's number divided by Avogadro's number times the natural log of 2, which is just equal to R times the natural log of 2. So we can actually put numbers to this. This is 8.314 joules per mole per Kelvin times the natural log of 2, and that calculates out to 5.76 joules per mole per Kelvin. Now let's just look at general entropy change for some common processes. For volume change, if the volume increases, the entropy also increases. We saw that happening when we allowed our 2 particles, 1 particle, 10 particles, mole of particles to expand into a bigger space. Temperature change. Consider that all energy is quantized. We only think about it really when we're talking about like electron energy levels, things like that, but energy is all quantized. Even stuff that we don't think about is being quantized. When you're at a low temperature, not all energy levels are available to you. But when you're at a higher temperature, more energy levels are available. Each energy level is a microstate, and so that means there are more microstates. So the bottom line is, as temperature goes up, entropy gets higher. Physical state. For solids, the particles are locked in position and they can only vibrate. Liquids, they can vibrate, they can rotate, and they can translate. There are more possible ways that the particles could be organized, more microstates. So the entropy is higher for liquids than it is for solids. For gases, they can vibrate, they can rotate, and they can translate just like liquids, but they can translate to way more different positions, which means the entropy of gases is higher than the entropy of liquids because there's more microstates. So that means melting increases entropy because we go from solid to liquid. Vaporizing increases entropy because we go from liquid to gas. But freezing and condensing, entropy goes down because we're going from more microstates to fewer microstates. Physical state. Most of the time, for solids and liquids dissolving in liquid solvents, entropy increases because the particles of the solute now have more different microstates that they can exist in. They're not bound only to be part of the solute, they can now be anywhere in the solution. For gases dissolving in liquids, it's the other way around. Now gases which were widely dispersed and had lots of different microstates that they could be in, they now are trapped inside of that solution, and that's actually a decrease in entropy for them. The last thing that we're going to look at is molecular complexity. More complex molecules have more ways to vibrate. So that means there are more available microstates, and that means the entropy will be higher. Here's an example. NO2, these are the number of ways that this could vibrate. N2O4 is a more complex molecule. There are many more ways that it could vibrate, more possible microstates. And so therefore, more complex molecules have higher entropy.